All right, now let's talk a little bit about oxidation numbers, which have to do with the charges that are present on different substances. So what exactly is meant by an oxidation number? Well, as I said a second ago, it's really the charge that's present on a chemical species, but we measure oxidation numbers different ways depending on whether things are atoms or ions or polyatomic ions. So if it's an ion, it's very easy. It's just whatever the charge is on that ion. If it's an atom, it's even easier, right? The oxidation number is 0 because the atom itself is neutral. The one that's a little more complicated is a compound or a polyatomic ion. And so here we have to look at what the charge would be on each individual atom if it were to be an ion. So what I'll do now is I'll show you how you can determine the charges for different ions. Excuse me. So for ions, in groups 1A through 8A, which are the alkaline metals, alkaline earth metals, all the way down to the noble gases, okay, the charges there correspond to what you would expect based on their positions in the periodic table. In other words, group 1A is +1, group 2A is +2, 3A is +3, group 4A is ±4, group 5A, then it starts to get negative. -3, group 6A is -2, group 7A, the halogens, -1, and then the noble gases, group 8A, those are all 0. Okay, and so that's what I mean by these numbers here. If I'm dealing with the transition metals, which are in the middle, right, the Bs, there I use the Stokes system. So for the Stokes system, we're going to use Roman numerals to represent the different charges. Okay, so in the Stokes system for these charges, if I see something like Fe and then parentheses II, that tells me that the charge on this iron is Fe2+. If I saw FeII, Captain, then it's Fe3+. So now let's talk a little bit about the rules for these oxidation numbers. Okay, when I have these compounds, the oxidation numbers have to add up to whatever the total charge is going to be on my compound or in my substance. So if it's a compound, they have to add up to 0 because the whole thing has to be neutral. And if it's a polyatomic ion, then they have to add up to whatever the total ion's charge is. In other words, if I have a polyatomic ion with a charge of +1, then all of the oxidation numbers together have to add up to +1. I can usually figure out where things are from the periodic table, but as a guideline, I can also use certain rules of thumb. Like, for example, for the halogens, most of these things tend to be -1, including fluorine, right? Fluoride is almost never anything other than -1, okay? And hydrogen is almost always +1, okay? The only exception is if I combine hydrogen with some kind of alkali metal or an alkaline earth metal, in which case the metal itself gets a charge of +1, and then the hydrogen is going to be -1. These are called hydrides. So they're rare, but they do happen on occasion. Oxygen is typically -2 in terms of its oxidation number, but it is possible for oxygen to have an oxidation number of -1, in which case it's something called a peroxide, or it can even be a fraction of -0.5, in which case it's something called a superoxide ion.